our, excellent.
Oh,
So our speaker is Dr. Hiroshi Inoue, Dr. Inoue from
eh,
Kyushu Sangyo
yes,
University. Sangyo, maybe it is state, yes? That's
yes.
Hiroshi, yes. So Kyushu State University. No, here it is written title. No, so please, you can begin. We are listening to you. Thank you very much for your
Yes.
agreement to give a talk. So please begin.
Okay. Thank you very much for the invitation of Moscow University. I feel
Mhm.
so happy to get the chance to talk about my studies and my ideas.
Good.
And so sometimes it is difficult for you to hear my English. Uh,
No, no. Our English is
yeah.
also not perfect, so we shall understand each other. Yes, and
So
your English, as far as I hear, is okay, much okay. So
as
please,
possible, I speak slowly and clearly. Please
good,
listen, relax, and
good.
carefully. Thank you. I start my
Yes,
presentation.
start.
The title of my talk, Introduction to Unbounded Observable Algebras.
I'm sorry, could you sharing the screen? As far as I can
Uh,
see,
so, please
Oh,
keep my keep the pin my
I see.
window.
Yes. The pinning it. Okay, I got it.
Pin.
Okay, yes,
Okay.
thanks. Yes, now it's better.
Yeah.
Thanks.
Now I share not share my window, but please keep pin my window.
mhm.
Okay. So
Okay,
okay, no problem.
no problem. Just to begin with
Okay.
text. Yes.
Yeah. And so
Okay. Mhm.
my talk contents number one, introduction, motivation, our research, future task. Okay.
Good, good.
So main purpose of my talk. In this talk, I shall introduce my studies and ideas about the unbounded generalization of Tomita's observable algebras. In particular, I shall talk about the motivations of our studies and structure theory and decomposition theory of unbounded Tomita's observable algebras. I briefly introduce our results. In detail, please refer the following. I prepared references 3. One is Atsushi Inoue has published Springer lecture note. This is original.
Mhm.
Started. So it begin. I begin this research from 2021. Yes. Okay. So we continued to research unbounded generalization because after I will talk, Tomita's observable algebra is bounded case. So we consider the unbounded case. So now I continue this study. So I shall talk about this study. Okay. So I want to talk about motivations. In quantum mechanics, self-adjoint operator A on the Hilbert space H represent observable, describe given quantum system, represent.
Mhm. Mhm.
Mm.
Prego.
And
Okay.
unit vector X in H represents state of the system. And this symbol is inner product between AX and X, is expectation of the observable A in the state X in quantum mechanics. Usually, operator observable A is mapping to the state X. Namely, A determines the unique state X. But this is motivation when the physical phenomenon happens. That is, I want to say, operator observable and state, no relation. For example, operator observable A is not mapping. That is, A does not determine the unique state X. This is a problem. And then how can one approach this phenomenon mathematically? It is motivation. So Tomita's ideas for this question, Tomita considered a trio as observable. Now, A equal A0, X star. Now, A0 is bounded operator. X is element of Hilbert space Ha. And Y star in Ha star. Ha star is dual of Ha.
Functional, yes.
Yeah. Tomita introduced algebraic and topological structure in T star Ha. Now, T star Ha is a set of all trio observable in Ha, which became a Banach star algebra. Tomita called star algebra of T star Ha is a T star algebra in Ha, and Tomita calls, and closed star algebra of T star Ha is CT star algebra in Ha. Atsushi Inoue has introduced this theory in reference 1. Reference 1. This. So, this is motivation of our research. The operator part of Tomita's observable is bounded operator. Now, bounded operator. Yes. However, operator observable in quantum mechanics is unbounded. So from this reason, we consider the generalization Tomita's observable algebra to unbounded Tomita's observable algebra. So I continue this study. So in detail, let's say be a dense subspace in the Hilbert space Ha. We put A equal A0 Guji eta. Now A0 operator part A0 is element of L-Dagger day. L-Dagger day is star algebra. Star algebra of the set of all closable operators X in Ha from day to day, satisfying this. Its definition. And Guji and eta in day, then subspace day. And so we called A this trio. is an unbounded trio observable. Okay, on day. So, T dagger day is the set of all unbounded trio observable.
Mhm.
On day. Become star zebra without identity from following operation and involution dagger. Now A equal A0 G eta. B0 equal B0 チェータ解。So A plus B equal A0 plus B0 next part グジplus イータチェータで、next part イータスター plus カイスター。Alpha A is this. AB equal little bit complement. A0, B0, A0 theta. This link is operator part is A0, B0. A0, B0. Next part is A0 theta. Next B0 eta star. It links. And involution of A is this. Then T dagger they become star zebra without identity. We call a star sub algebra of T dagger day is called T dagger algebra on day. We research T dagger algebra. So bounded case. Okay. So next for unbounded trio observable. Now I is T dagger algebra. Then we for element of A in R, we put pi A equal A0, lambda A equal G, and lambda star A equal eta star. Then pi is star representation of R on day, and that is star homomorphism of R into L dagger day. And vector part, lambda is vector representation of R into day. That is a linear mapping of R into day satisfying this. Okay. Similarly, lambda star is vector representation. So, this study now I introduce T dagger algebra and pi A, lambda A, lambda star A, and this is representation. So this we use this notion. We investigate to T dagger algebras. This studies the studies of this unbounded observable algebra is closely related to operator algebra on Klein space and unbounded Tomita-Takesaki theory. In detail, please refer to Atsushi Inoue has published Tomita-Takesaki theory in algebra of unbounded operator. And positive linear functional on star zebras without identity, closely related. Okay. This positive linear functional on star algebra is I introduce Ries form or sesquilinear form. So please refer to reference 2 or 3. So our results at first structure of T-Dagger algebras. At first, we defined the notion of CT-Dagger algebra as a uniformly closed T-Dagger algebra. So we implement uniform topology in detail. Operator part pi R is T-Dagger algebra. Author algebra pi R implement K-psi star uniform topology. And lambda R to implement to T pi R topology. This topology is graph topology. So we define the notion of closed for T-Dagger algebra. So please, in detail, please refer to reference 2. So next, we consider commutant of T-Dagger algebra.
Sorry, lambda A is a set of vectors, right? Am I right? Lambda of A. It's inside of D. Is it?
D?
Lambda of A should be inside of D, as I guess, right? I mean, domain D. No. Lambda of A, the image of lambda of the algebra, they are consist of vectors, right?
Vector? Sorry,
You got to okay. Well, lambda of A, if you're applying lambda, there's some set of vectors, right? Is inside of D.
Yes.
Is it?
Now, R is T-Dagger algebra on day. So,
yeah, that's true. Yeah. So lambda of A is inside of D, as I guess. Yes.
Yes.
Okay. Yeah.
Okay. Okay.
Yes, that's true. Okay, thanks.
Thanks.
Okay.
So I continue the presentation. Commutant. Next, we consider the commutant of T-Dagger algebra. Now, this is new notion. R is pi self-adjoint. This definition is now I consider Torio. So we introduce to the notion of operator part, vector part, respectively. So this pi self-adjoint is under operator part and condition for operator part. This definition is the author algebra pi R on day is self-adjoint. That is, they equal this. Next, we consider operator part pi R. Now, weak commutant of pi R. This we denote this symbol. The definition is this. So then, weak commutant of pi R is a Von Neumann algebra on her, and invariant to day to day. Okay. So next, we define a commutant of a T-Dagger algebra denoted by RC by this little bit complement, where new symbol K sharp equal is the involution of K. Okay. Then we commutant of R is a CT star algebra on her. Now we can define the commutant T for T-Dagger algebra. Next, we define bicommutant. This denoted by RC tau by RC tau equal A in T star her such that AK equal KA for K in commutant of R. Then bicommutant is CT star algebra on her. Okay. So now we define the basic notion closed, commutant, bicommutant. Next, we investigate the structure of pi self-adjoint T-Dagger algebra. Now I add one comment. Why pi self-adjoint T-Dagger? We consider pi self-adjoint T-Dagger algebra because we can consider many situations because now consider trio operator part and vector part. It's very complement, and we can add the give a condition for operator part or vector part or another vector parts. But we want to construct the outline of basic theory. So as possible, we want to investigate simple case now. So this talk is maybe small part, but we can consider many parts. So now I want to outline. I want to talk about outline. Okay, so this is at first we consider the structure of pi self-adjoint. Now in my talk, pi self-adjoint T-Dagger algebra. So we define some projection in weak commutant of pi r. Pi r is operator part. So PR, PRC, PRC tau, NR, NRC tau. Now this is the projection on closed subspace.
Yeah.
In her generated by higher day. Similar definition. And where new symbol NR equal the element of A of R such that operator part is 0 and NR theta equal biconcomitant element A such that operator part is 0. Then N1 is a stylier of R, and NR theta is a CT-star algebra on her. So then we can get the result. Theorem 1 is PR equal PR theta equal I minus NRC in center of weak commutant. And PRC equal NR, I minus NR theta in weak commutant. And NR not in weak commutant. And NR not equal NR theta in general. And this relation. Please refer to reference 3, example 1. We give this example. Okay. So next, we can we define the following notion. Now we defined some projection. We defined the notions about projection. A is non-degenerate. Its definition is PR equal I. Regular equal PR, PRC equal I. The semi-simple PRC equal I. Weak semi-simple, many notion. A singular is NRC equal I. Of course, this NRC equal 0. This is NRC equal 0. NRC equal I. So PRC equal 0. Okay. I is strongly singular. Its definition is NR equal I. So for semi-simplicity of T pi self-adjoint T-Dagger algebra, we have the following. Now, semi-simple is PRC equal I. Theorem 3 is let's R be a pi self-adjoint T-Dagger algebra on day in her. We consider the following statement. Number 1 is R is regular. That is PRC equals I. R is semi-simple. That is PRC equal I. Number 3 is there exists a subset Guji alpha of self-adjoint element of day satisfying this. And now self-adjoint element is Guji self-adjoint element. Of day. Its definition. Foster algebra. I Guji is essentially self-adjoint. So this symbol, is restriction of pi I Guji. Okay. So and 4 is weak semi-simple is R equals 0. And 5 is NR. と、sorry, this is element is only 0. And 6 is pi operator part is mapping, namely lambda a equals 0 whenever pi a equals 0. So this statement is operator observable. Operator observable is mapping state part. State. So operator observable and state is good relation. So then this relation is hold. Hold. So maybe it is important is semi-simple is 2. Then weak semi-simple. Equivalently this and equivalently this. So for semi-simplicity pi self-adjoint T-Dagger algebra, then operator observable and state part is a good relation. This theorem is very important for T-Dagger algebras. So furthermore, if lambda is dense in her, then this statement is equivalent. This statement is regular and semi-simple is equivalent. And if R is pi lambda self-adjoint, this is new word. This self-adjointness is definition is this. Operator part is self-adjoint and vector part is lambda self-adjoint. Lambda self-adjoint is the pi invariant subspace lambda R in day is essentially self-adjoint. That is the closure the Osa algebra this on lambda day is self-adjoint. Okay. So then, of course, pi lambda self-adjoint is stronger than pi self-adjoint. Operator part and vector part, we give condition. So then, this number 2 and number 3 is equivalent. Okay. ここか。ここか。で、if R is CT star algebra, that is bounded case. Bounded case, CT star algebra. Operator part is bounded. Then this statement is equivalent. Equivalent. Okay. So next, for singularity of pi self-adjoint T-Dagger algebras, we have the following. This part, singularity. Let's be a pi self-adjoint T-Dagger algebra on day in half. Consider the following statement. R is strongly singular. That is NR equal I. R is singular. NPRC equal 0. And this equal dense subspace. Then this relation is hold. Of course, singular not equal strongly singular. Please, we give the example. Please refer to 3, example 2, 3, and 3. Please refer. So next, I want to talk about decomposition theory. Now, I presentation about structure of T-Dagger algebra. Of course, two cases, singularity and semi-simplicity. Next, decomposition of T-Dagger algebra. In this section, we consider whether pi self-adjoint CT-Dagger algebra is decomposed into the regular part and singular part. Okay, let's be a pi self-adjoint T-Dagger algebra on day in half. E be a projection in weak commutant of pi r. For any A, we put tau ER, tau EA equal this. The new EA equal this. And the set of tau EA, tau ER, we put new ER equal the set of new EA. Then it is clear that tau ER is a pi self-adjoint T-Dagger algebra on day, and new ER is a T-star algebra on half. In reference to the next slide, the following results for the decomposition of T-star algebras, that is bounded case, have been shown. Proportion 6, this theorem, this proportion. In R is CT star algebra on half, and PR is the CT star algebra generated by this, and put ZR equal A in R such that AX equal XA equal 0. Then the following hold: PR equal tau PR R. ZR equal new I minus PR equal Z new ZR. The next part is R is decomposed. We is decompose PR plus ZR equal tau FR NR. Here, in bounded case, we can decompose T star algebra. But I investigate unbounded case. So whether we can get the similar result or same result. So I want to talk the related result. So here we consider whether the result of proposition 5 hold for CT Dagger algebras. So let's be a pi self-adjoint T Dagger algebra, unbounded case. Then we decompose the projection PRC and NRC tau as follow. F is PR PRC, VR is this, SRC tau is very complement, but and ZRC tau equal this. Then all these projections are Von Neumann algebra in weak commutant pair. And I call this. Furthermore, we have A equal trio observable equal decompose this. But I have big problem. Differently from the case of CT star algebras. Very different. Because we don't know whether this is we don't know whether this is elements of R. This is very big problem. So when under what condition this part is an element of R. So we consider the T-Dagger algebra, tau PR and nu I minus PR. So we can get we have the following result for position 6. Let's I be a pi self joint T-Dagger algebra and PI the CT Dagger algebra generated by this. Then we have the following statement. Okay. This PR, this relation and they don't necessarily coincide. But okay. Nu I minus PR equal nu ZRC tau and this intersection equals ZR. This ZR is the definition is this. So I prove this proposition. I have a question. I have a question arise. So question 1. PR when under what condition PR equal tau PR? Question 2 is tau PR is contained R. So that is this. So refer to reference 3, example 4 and 5. Question 1 is not necessarily true. But for question 2, we have the following result. Let's R be a pi lambda self-adjoint CT Dagger algebra. Suppose that PR times 0 times we put this. And then tau PR. This question is solved. And R is decomposed. R can be decomposed this part. We have the main result. So for decomposition, next we another condition that is strongly non-degenerate self-adjoint T-Dagger algebra. Next we consider we have the following. Now, R is strongly non-degenerate. This definition is if subspace of R generated by pi r day is dense in this, and R is self-adjoint. Its definition is Osa algebra pi r is self-adjoint, and Osa algebras pi r restriction of lambda r, and this are essentially self-adjoint. Its definition. Then we have the following. NR equal mu NR, and tau I minus NR is weakly semi-simple CT Dagger algebra. Contained, this is important, in R. And I's can be decomposed this part. Okay. So, decomposition is into, of course, I want to say again, of course, maybe we can consider for decomposition of for example, non-degenerate self-adjoint T-Dagger algebra, or another notion. But now I introduce in strongly non-degenerate self-adjoint or high lambda self-adjoint of T-Dagger algebra. So maybe I more study, maybe I get more results. Maybe. Maybe. But now I get this results. So so at finally our result application. I want application. Application to studies of positive linear functional on star algebra, of course, without identity. So now F is positive linear functional on A, and pi F, lambda F, ha F is GNS construction for F. Now pi F is unbounded star representation of A in Hilbert space, ha F. Lambda F is vector representation of R into the domain day pi F of pi F. And then we put RF equal trio. Pi FA, lambda FA, lambda FA star star. Then pi F is T-Dagger algebra on day pi F in Hive. And so I will more study this application. So maybe I think our study, maybe not maybe, it's clear.
Yes.
Our studies of T-Dagger algebra can be applied this of positive linear functional on star algebra. So please refer to reference 2. So future task. So I investigate decomposition theory for T-Dagger algebras. This is continued. I want more detail for decomposition theory. And I am prepared to submit paper on polar decomposition and functional calculus. for T-Dagger algebra. I have some results, but I feel very, very difficult. But complete. So I preparing to submit this paper. And so near future, I will investigate relationship between T-Dagger algebra and unbounded Tomita Takezaki theory. So I want to consider automorphism groups for T-Dagger algebra and dynamics for T-Dagger algebra. So maybe 1 year or 2 years, I get the results. I will get the results. So many, I feel this is Tomita Takezaki theory. No. Tomita's observable algebra is very new story. So I feel many, I want many idea and many collaboration and so many application we can consider. So I feel very interesting the research this field. So if everyone interested, if
of course,
so
enjoy, yes.
Yes. So I'm sorry to my English is very
no.
So
it is better than our English. Dear Firas, yes.
Little bit
very understandable and clear. Yes, don't have any,
so little bit short time, but I talk is finished, and thank you for your attention.
Thanks a lot. So, what about questions? Usually, Anar, as Benny Creek in Babel's novel, always have questions.
Could you explain briefly just where did it come from, lambda f, vector representation of a positive functional? I didn't get it properly. If you can, by somehow.
Don't be quick. Yes.
Lambda f. Yes, lambda f, vector representation of A. Where did it come from? How did you get it from positive functional f? Is it possible to explain?
Sorry. This f is positive linear functional.
Yes. Okay. Yes. What about lambda f?
Lambda. Lambda is?
Yes. Lambda, you mean?
Yeah. How you can define lambda f? I mean, briefly, where did it come from?
Okay. So, but this part is in detail. Please refer to reference to. I detail. Sorry.
Okay, yeah. No, that's okay.
Sorry. I little bit forget.
Yes. Okay. Yes, I understand.
Sorry.
Yeah. It's okay. Yeah. Yeah. By somehow it's appearing. Yes. Okay.
Other questions? Maybe somebody? Yes? No. So let us thank again Dr. Hiroshi Inoue for indeed a very, very interesting and clearly, presented lecture. Yes. So our next lecturer is just Professor Anar Dossi. Yes. And he, agreed to be our next speaker, which we are very indebted to him. So we meet exactly exactly after a week. So thank you everybody who is present, and so next week. Okay. Bye-bye.
Next Friday?
Next Friday, yes. Next Friday, 6 o'clock in Moscow times. Because it is international, as Greek said, the after feast.
Yeah, the same Cyprus time.
Okay, okay. But in your university, time is more or less the same, I suppose.
Yes, yes.
In Moscow. Yes, yes. Okay. So bye-bye.
Bye. See you.
Bye-bye.
Bye-bye.